All right. So in the case of, with the last observation we made, which is that for continuous random variable, well, for probability distributions in general, we have countable, not uncountable additivity, but continuous random variables bring us into a situation where we have uncountably many possible outcomes. We asked the question, well, how do we actually calculate probabilities in the continuous setting? And the way that this is done is, remember, in the discrete setting, we have a mass function. So because there's discretely many values, what we do is we have a specific probability that's assigned to each value. And because there's at most countably many values, by countable additivity, we just add up those masses for whatever event, the masses corresponding to whatever event we're interested in, and we get the probability of the event. We can't do that for events in the continuous setting because the event itself might be a union of uncountably many outcomes. So it's not we can't describe these probabilities by a mass function, because in general, as we saw in this example here, right here, the probability of any given point happening is 0. So the way we do this actually in the continuous case, what's called a density function. Okay, so the density function is the continuous analog of the mass function. And in fact, they're actually the same idea. If you think about the terminology we're using, that mass is, we're saying that there's some physical mass that we're thinking of them in terms of physical masses. We're saying there is a positive mass of weight being put in this one particular point. In the case of continuous variables, there is really no mass at any given point, but we think about the density of the mass, right? So how dense, how much relative mass is there in an area compared to others? And this is through what's called the density function. So a random variable has a continuous distribution. So let's assume, again, we have a probability space is underlying all of this. Random variable has a continuous distribution. If there exists a function f, we'll write it as f. Sometimes we write it f sub x to indicate that it is tied to x. Doesn't have to, though. It's from the real numbers, so it's the values that x takes to positive real numbers, such that the probability that x is an element, so the probability that the random variable falls in some possible subset, this is the same as saying there's some event occurs, is the integral over the subset of this function f of x dx. This is for subsets B and R. Specifically, the integral over all of R, so from minus infinity to infinity of f, is 1, because that is the probability, according to this, that x takes values between minus infinity to infinity, and that's has to happen because x is a random variable. So when we have a function like this, we call it the density of x. And so that density is saying this is how concentrated the probabilities of x are throughout the real numbers. So how can we think about this? So the way we think about this is that intuitively is that the possible values that x can take are anywhere from minus infinity to infinity. And let's call this f of x, right? Well, the integral, let's just say from a to b of f is the area under f between a and b. So if we have a here and we have b here, this is the probability, okay? And so this is the integral, and that is what we're saying is how we measure and how we express the probability that x is between a and b. So if x, so one way to think about this though is that, okay, if f, let's keep it as f sub x, okay, is continuous at a particular point, okay, then let's think about, let's look at x now. So this is x. And let's think about the probability that x is between little x and x plus a little bit. We'll write it as delta. So x plus a little bit. Okay. Well, that probability is, well, what is that? Well, it's technically the integral, but it's it's approximately. So one way to think about it is that it's approximately, well, look at this here. Let me try to highlight this. This curve here is pretty flat, right? And if you make delta really, really small because of continuity, there's not too far, you know, that the function can't go too far off in a small period of time, in a small area, in a small window because of continuity. So this is kind of like a rectangle. And if you look at it as a rectangle, right, the area of this rectangle is close to the area under the curve, right? But what is the area of the rectangle? Well, it's the base times height. Well, the height is approximately f of x times x, and the width is x plus delta minus x, which is delta. Okay. And so that's exactly how, that's essentially what we are doing in an integral, is that we're breaking this up into really small pieces. We're taking the limit. Well, now think about dividing by delta. So you divide by the length of x to x plus delta. Well, what is that length? It's just delta, which is, of course, fx x. Now, this approximation is only really valid if delta is small. So to formalize this, we would consider it as a limit, but intuitively speaking, we've already accomplished everything, is we think about taking a really, really small window around x. And if we do that, the probability that the random variable falls really close to x per unit area of the window, which is delta, is, well, technically, it's the limit as delta goes to 0 of 1 over delta integral x to x plus delta, which we've just shown is the density function evaluated at f. So the intuition is to say that if we look at the probability mass per unit is approximately the density, right? That's how we think about density, right? It's how heavy something is at an infinitesimal point. How dense is it? How much mass does it have above that point? So to define now remember the concept of the cumulative distribution function. So the CDF, or just the distribution function, of x. This is capital F. We subscript it sometimes for convenience by the random variable. It is a function now from real numbers to the unit interval, because this actually does give us probabilities, and it's defined the same way as before. It's defined as the probability that x is at most a certain value. But now in the continuous case, what that is that's exactly equal to the integral. That's exactly equal to the integral from minus infinity to x of the density dx. And the way we use this, we didn't actually use dense distribution functions much in the discrete case. We did see it a little bit in the geometric, and we did write it down in a few cases, but it was really of limited immediate use. It's much more useful in the continuous case, and we'll see that. And the reason is because if we consider taking it, we can calculate the probabilities of the random variable falling within an interval, so falling between x and little z here. The way we can do that, well, by definition, first of all, that's the integral from x to z of the density. But one way to think about this, so that we can think about it as, well, we first integrate, this is the same as integrating minus infinity. I'm sorry, this should not have an argument x, because we don't want that, because the limit of integration is involves an x, so we should be using y or something else. So we first integrate all the way up to z, but then we subtract off the piece all the way up to x. But if we do that, that's actually, in terms of the distribution function, that's distribution function evaluated at z minus distribution function evaluated at x. So that's how we would use the distribution function to calculate a lot of probabilities that we're interested in. In the continuous case, we're often interested in whether the variable falls within a particular interval. And then finally, if f, the distribution function, is continuously differentiable, or if it's everywhere continuous and differentiable what's called, well, differentiable almost everywhere at all but finitely many points, then the difference between of the distribution function between z and x is, by definition, it's the integral from x to z of the density, but in fact, the density is just the derivative of the distribution function. So when we have a nice distribution, and oftentimes we will, this is by the fundamental theorem of calculus, FTC, fundamental theorem of calculus. When x, the random variable, has a nice distribution, and in very many cases it will, we'll be able to, if we can express the distribution function in a nice way, and it's a continuously differentiable function, then we can derive the density by taking the derivative of the distribution function, and that'll prove useful in several cases, as we'll see.